Swayam Prabha. Digital India. Educated India.
Welcome back. So this is the second slide set in the computer arithmetic chapter. So since the chapter was long, we divided it into two slide sets. This is otherwise the fourth lecture in this series. So we had promised to discuss a couple of things. We had promised to discuss division and floating point operations, namely addition, multiplication, and floating point division. So let us now divide. So let us only consider positive numbers in our discussion, because dividing negative numbers is kind of tricky. Well, it's tricky in the sense that we need to first understand that when we are doing integer division and there's a negative number involved, there are different conventions for the remainder. Some conventions say the remainder is always positive. Some conventions say that the remainder has the same sign as the divisor. So actually what most libraries or processors would do is that they would first convert the numbers to positive numbers, do the division with positive numbers, and then adjust the remainder according to the convention. So again, there are different ways of doing it, but let's just stick to positive numbers in our discussion because number one, is simpler. Secondly, since division is a fairly long operation and it's not possible to have log n time algorithms very easily, it's okay to convert negative numbers to positive, do the division, and then adjust the signs. So let's now introduce some basic terminology. The terminology is like this, that when we are dividing, let's say that we are dividing n by d, right? So this is slash operator, same as integer division, n divided by d. So in this case, we'll have a quotient and a remainder. For example, if I divide 5 by 2, the quotient is 2 and the remainder is 1. So this can alternatively be said that n, which is the dividend, so basically the top number is called the dividend and this is the divisor, n is equal to dq plus r, where n is the dividend, d is the divisor. So we are essentially dividing the dividend by the divisor. We are computing n by d. Then we'll have a quotient. Quotient is a result of the division. For example, if we divide 100 by 20, the quotient is 5. If we divide 101 by 20, also in integer division, the quotient is 5. But in this case, the remainder will be 1. So there are two things. So division has two outputs, a quotient and a remainder. Both of them need to be computed. Now, let's take a look at some properties, right? In this equation, n equals dq plus r. So one property is that the remainder has to always be less than the divisor, right? So that has to be the case. The reason that that has to be the case is otherwise, the division is wrong. For example, if I divide 101 by 20, right? If I divide 101 by 20, the quotient cannot be 4 and the remainder cannot be 21. So it basically means that the division has not been done correctly. So the quotient has to be 5 and the remainder has to be 1 in this case. So r is less than d. Furthermore, r is greater than or equal to 0. So we always have a positive remainder if we are considering only positive numbers. We can then, so let's remember these properties. We'll refer to this as property 1, the property that the remainder is less than the divisor. The other one we'll refer to as property 2, which says that the quotient q is the largest positive integer that satisfies equation 1. Okay, I should probably call this as equation 1. Sorry. Right, that satisfies the equation and this is equation 1. So the quotient is the largest positive integer. So this is also obvious. So again, if I'm dividing 101 by 20, so 5 is the largest number that satisfies the equation 1 and essentially the equation and the property 1. So why is this the case? Because 5 times 20 is 100 plus 1. 6 will not do, because if I have 6 times 20, then dq will become 120, so r has to be minus 19. But what we understand from here, from property 1, is that r is always greater than or equal to 0. So as a result, it cannot be negative. So both of these properties are otherwise obvious, but it's nice to write them down, because any division algorithm has to obey both of these properties. And so these are also sufficient properties, not necessary, but sufficient properties. We need to find, so q is the largest positive integer which satisfies the equation, and also property 1 needs to hold, where r is less than d and r itself is greater than or equal to 0. So we need to ensure that these two properties 1 and 2 always hold. So let us, so maybe the way that we should modify this slide is that satisfying equation 1 and property 1. Right, so that will fix this slide. Alright, so let's do one thing, let's do a little bit of math. So let's start with our division equation, which is n equals dq plus r, and let's assume that the quotient q, which is of course represented in binary, the bits are qn to q1. So what we can do is that we can divide the quotient, so we can sort of break it into two parts. One is qn times 2 raised to power n minus 1 plus one number which consists of the remaining n minus 1 bits. Right? So we have also done this before in chapter 2. So one good idea would be that somebody who has forgotten what we did and learnt in chapter 2, all about bits and floating point numbers and so on, can go back to chapter 2 and refresh the knowledge, because we'll be using many results here. So what did I do again? I considered the quotient to be an n-bit number, and I take the MSB out. So I say qn times 2 raised to power n minus 1 plus the number that is left out of the rest n minus 1 bits. So if I break the quotient in this way, I have one component over here, which is the first n minus 1 bits of the quotient. I have one more component over here, which is divisor times this thing, and this thing is qn is the MSB of the quotient, most significant bit, times 2 raised to the power n minus 1 plus the remainder r. Now what I can do is that I can take this term to the left side and have n minus d times qn to 2 raised to power minus 1 is equal to d times, so let the number of the quotient, so let the number formed by the first n minus 1 bits of the quotient, let's call it q dash. So what we'll have is d times q dash plus r, right? And let me call this term over here as n dash. So what we see is that this equation looks very, very similar to this equation, right? There is no difference at all in the structure, but there is a little bit of difference in the terms. So the remainder is the same, mind you, and the divisor is the same, but the quotient in this case this is the n-bit quotient. In this case, it's the same quotient, but the first n minus 1 bits. In this case, it's the original dividend. In this case, it's the dividend. The dividend is, so what's the dividend in the uppercase? It is the original dividend n minus the divisor times the nth bit of the quotient times 2 raised to power n minus 1. Right? So this is the dividend that is being used. So what we have done is that if we can somehow figure out the nth bit, right, the most significant bit of the quotient, if there is some way of figuring that out, then what we can do is that we can compute a new dividend, which is n dash, and solve a smaller division problem where the quotient has n minus 1 bits. Alright? Similarly, I can then have one more, I can carry on in this same manner, same fashion. I can then have one more equation, which is q dash dash plus r, where this contains the last n minus 2 bits of the quotient. If I have some way of again figuring out the n minus 1th bit of the quotient, I can come to this equation. Similarly, I can go down, 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 down till I sort of reach one point. So let me maybe put a star. Sorry, there's a bad star. Let me erase that. Yes, a better star. Till I reach one point where this is the divisor times the first bit of the quotient q1 plus r. Right? Now, at this point, if I have some magical way of figuring out what is the least significant bit of the quotient, then what will ultimately remain is what will remain is at the end, we'll only have the remainder left. So we can, what's left will be the remainder, and at every point we'll get one bit each in the quotient, starting with the nth bit till the first bit. All right. So what we are doing is that we are gradually reducing the division problem from a problem of dividing, from a problem of computing an n-bit quotient to a problem of computing an n minus 1 bit quotient to a problem of computing a 1-bit quotient, right? So at every stage, we are sort of making the problem slightly smaller and slightly simpler. Till at the end, we need to compute a single bit, and finally, we'll be left with the remainder. So this sounds like a good plan. It is just that the secret sauce is missing. And the secret sauce here is how on earth do we compute how on earth do we compute the nth bit of the quotient? Because if we can do that, then we'll be able to solve the entire problem, because at every stage, what we will do is that we will keep on reducing the problem to a smaller version till we reach the end. We get all the bits of the quotient, and what's left will be the remainder. So let's see. Right? How do we reduce the original problem to a slightly smaller problem? So what is the main issue? The main issue here that is bothering us is how to find Qn, the nth bit, the most significant bit of the quotient. How is that to be found? So let's think of it. So it's simple, but let's sort of look at it from a distance. The nth bit of a quotient, so it's after all a single bit, right? So if it's a single bit, how many values can it have? It can have only two values, 0 and 1. So since there's two values, what we can do is that we can try a brute force approach. So we can try both the values, both 0 and 1. So let's first try 1. So if n minus, so what do we need to do? We basically need to compute n dash is equal to n minus d times q, right? If qn is equal to 1, then n dash becomes equal to n minus d times. So what we can do is we need to compute this, and since we have to maximize our quotient, so why do we need to maximize our quotient? It is property number 2, that we want to maximize the largest positive integer, right? So since we want to maximize our quotient, what we would like to do is that we would try to set qn is equal to 1 if the new dividend is still positive, right? So if n minus d times 2 to the power n minus 1, if that is still greater than equal to 0, then it means that the nth bit of the quotient can be set to 1, and we, in a sense, will maximize the quotient, right? So then fine, if this is the case, we set Qn is equal to 1, because our original aim was to have a quotient as large as possible. And if we can get away with setting the nth bit of the quotient as 1, this means that it is the right guess, it is the correct guess, and we will set the new dividend to be this and solve a smaller division problem, right? Where we'll get the rest n minus 1 bits of the quotient. However, if this term is less than 0, then it means that the largest bit of the quotient cannot be 1. Hence, we set it to 0. We set what to 0? We set Qn to 0. Alright. So what we have done is that we have thus computed Qn, and we have also reduced the problem. Problem was initially to compute an n-bit quotient. Now we are computing an n minus 1 bit quotient, right? So how are we doing that? We considered the quotient to be an n-bit number. We made two guesses for Qn. One guess was 1, the other guess was 0. With 1, we tried to see that whether the problem still remains valid if we make a guess of 1. And if it remains valid, we agree that Qn should be 1. So we set it to 1, the nth bit of Q. Otherwise, we set it to 0. And then we compute the new dividend, which is n dash is n minus d times 2 to the power n minus 1 times Qn, right? And we proceed recursively, which means that we call the same process over and over again, albeit with reduced or smaller arguments, till we are left with a single bit. Alright, so the long and short of this slide, the summary of this slide, is that we now have a method of computing a single bit in the quotient, which is the most significant bit. We have a method. What we do is that we first make a guess. We see if, whether if it's 1, it'll work or not. The reason for this is that we want to maximize our quotient. If n minus d times 2 to the power n minus 1, if this number is greater than or equal to 0, then it means that the quotient can be set to 1. Otherwise, it means that the quotient cannot be set to 1. And in this manner, we proceed and we gradually reduce the problem. Alright, let's proceed, but before, let's proceed and then I'll show an example. Okay, so before I actually show the mechanism, let me make a quick trip to the previous slide. And let me delete all of this stuff and explain with a very quick and small example. So what I do, so let me try to divide. So let me consider a 4-bit number system. All right. So in this case, n, which is the number of bits in the number system, that is equal to 4. Furthermore, let me try to divide 13 by 4. No, let me try to divide 13 by 3. So what is the quotient? Well, the quotient in this case is 4 and the remainder is 1. What is the binary representation of the quotient? It is 0, 1, 0, 0. Alright, so let's try to do something. So in this case, n is 13. The divisor is 3. So let me first, in the first iteration number 1, let me try to compute n minus d times 2 raised to power n minus 1, which is equal to 13 minus 3 times 2 to the power 4 minus 1, which is 2 cubed, which is 8. So 13 minus 24 is less than 0. So as a result, we will set the most significant bit of the quotient to be 0. As we can see, this is the correct answer. Alright. So in this case, n dash, which is the new dividend, will remain the same as the old dividend, which is 13. Fine. After that, let us go to the next iteration. So in this case, let me do the same thing, 13 times. So in this case, n was 4. Now in this case, n will become equal to 3 because we are moving to a smaller number system. Right? So it's the next iteration pretty much. So in this case, what we do is that we do 13 minus 3 times 2 raised to the power 3 minus 1, which is 2 to the power 2, which is equal to 1, which is greater than or equal to 0. So as a result, we set Qn is equal to 1. And as you can see, this is exactly, sorry, not Qn, but this is Qn minus 1. So let's call it Q4 and Q3. That's slightly easier. The fourth bit of the quotient and the third bit of the quotient. Just quickly erase this part. Erase this part. So let us say that this is Q4 and this is Q3. Fine, let's go to the next iteration, which is iteration number 3. So in this case, so what is n dash? N dash is equal to 13 minus 3 times 2 square, which is 1. So then I'll again compute 1 minus 3 times. Okay, so in this case, n again becomes 2. So 2 to the power 2 minus 1 is 1. So which is less than 0? So basically Q2 is equal to 0. Well, so again Q2 here is equal to 0. So we have computed this properly. So we go to the last iteration, which is the fourth iteration. See here again the new n dash is equal to 1 because no change was made in the last time. So what we need to compute is 1 minus 3 times 2 to the power in this case it's 1 minus 1, which is 2 to the power 0 is 1. This is again less than 0, so we can say that Q1 is equal to 0. So as you can see, Q1 is equal to 0 over here. So what we basically get to see is that we have computed the quotient, which is 0, 1, 0, 0 correctly using this method. So we'll get to see some more examples of this method, but this is at least a quick way of explaining how this method works. So how will we actually implement it in hardware? Well, very similar to the iterative multiplier. So we'll have the divisor here in D initially, so we'll have 2 registers here, and the same way we had for the iterative multiplier, and for the purposes of shifting, they act as the same register. So initially V will hold the dividend n and U will contain the number 0 and D will contain the divisor. So here instead of addition, since division is repeated subtraction, every iteration will subtract, possibly subtract D from U and write the value back to the U register. Alright, so let's take a look at the algorithm, which is very simple. It's called the restoring algorithm. So the restoring algorithm, what it does is that we divide two 32-bit numbers. 32, 64 doesn't matter. So the input is the data, the divisor is in register D. So as you can see, the divisor is here in register D. The dividend is in register V, so which is this register. The dividend is loaded over here. And so if you left shift, then essentially this bit will come here. And at the end, we want U, the register U, to contain the remainder, and register V to contain the quotient. So U will at the end contain the remainder, that's what we want, and register V, we want it to contain the quotient at the end. Alright, so what we do is that we run an iteration, a for loop for 32 times for I equals 1 to 32. That's all that these lines do. is that you run a for loop for 32 times. So then we left shift the UV register the same way we did with the case of the multiplier. So in that case we were right shifting, in this case we left shift. So we do a left shift by 1 position. Then what we do is we subtract D from the register U. So we subtract the divisor from the register U. If U is greater than equal to 0, right, then we set Q to 1. Q is a temporary variable, we set it to 1. Otherwise, what we do is we restore the value of U. So U becomes its old value. That's the reason it's called a restoring division, because initially we subtracted, but if we find that the result has become negative, then what we do is that we add the value of the divisor back to U, right? So U becomes its old value, and we set Q to 0, and then we set the quotient bit, the least significant bit of V, to Q. Alright, so that's what we do. Okay, so before we look at an example, it is very, very important for me to give a certain feel of why this algorithm is working. Because to get a feel is very important. So let me use some real estate here to draw. So let us consider the two registers. The two registers that I have are registers U. Okay, let me just write them at the corner. I need some space. And registers V. So initially the dividend is completely loaded in register V till we come to this line in which the dividend is shifted to the left, right? So the dividend is shifted to the left by 1 position. So basically the dividend occupies, so let's consider this much to be 1 position. So pretty much occupies this much, right? So let me call this the dividend portion. So I'm just considering the first iteration, but all iterations we'll argue in the same fashion. So this is the dividend N. Of course, there's some amount of space created over here, but let's ignore this. So this will not come into our calculation, so can be ignored. Now what I do is that I subtract the divisor from register U. So if I consider this part as the divisor, right, from register U, and if I consider this as an entire number starting from here, right, so to the right of this I ignore, but let's say starting from here, if I consider this much to be a full number, what I'm essentially computing is I'm computing an n dash which is equal to n minus the divisor. So mind you, the divisor as compared to the beginning of this number is shifted to the left. How many positions is it shifted? So basically this entire distance is n bits. So since and this distance here is 1 bit. So as compared to the beginning of the place where our dividend starts, right? So as these bits we have ignored because we have left shifted it anyway in this line. So as compared to the beginning of where the dividend starts, the divisor is n minus 1 positions to the left. Alright, so if you are looking at the screen, the divisor is n minus 1 positions to the left. So when I'm doing the subtraction, u is u minus d, what I'm essentially doing is that for this number, which begins from the beginning of the dividend till the end of register u, if I so this number at the beginning is all zeros, so let it remain in that fashion. So this number that I have, I'm essentially subtracting the divisor multiplied by 2 raised to the power n minus 1. Right, and since, well, I can maybe clean up the minus 1 a little bit. Okay, and since I initially assume that I am multiplying this, the quotient bit is 1, I can add qn, where Qn is 1. Well, so does this particular equation look familiar? It definitely should, because this equation is exactly this equation over here. So let me maybe a good idea to clean the slide. This is exactly this equation, right? This is the same term. N dash is n minus divisor times 2 raised to power n minus 1 times Qn. So this is exactly what we are doing, that we have computed the new dividend, and the way we have done that is via this particular hardware mechanism. But in a sense, what is being computed inside is the old dividend minus the divisor multiplied with 2 raised to power n minus 1 times Qn, where we are assuming that the quotient bit is 1. So this is, this is just a hardware implementation of the algorithm that we have described. Now if the new value of u is less than 0, which means that this new dividend is not valid, then we will set the quotient bit to 0 and restore the value of u, right? So we don't want a negative dividend, so we'll restore it. That's what we have been doing. Otherwise, if it's greater than or equal to 0, well, fair enough, we have computed the quotient bit to be 1. So once we have done that, the quotient bit that we compute, that is set to this unused space over here, which is Qn, right? Because this space is anyway not used, we are not factoring it into the dividend, so this will become Qn. So gradually so now let's consider the next iteration, right? So this is the first iteration. If I consider the next iteration, the situation will be very, very similar. I'm just drawing a smaller version of the U and V registers. The situation will be very similar. We will start our dividend from a newer position, and there will be 2 bits here instead of 1 bit. And we can consider the rest as a new dividend n dash that was computed in the previous iteration. 1 bit over here will be the nth bit of the quotient Qn, which we have computed, and this bit will be Qn minus 1 that needs to be computed in the current iteration, which is the second iteration. Then we can do exactly the same, right, in the next iteration, and compute Qn minus 1, exactly the same logic. And the same logic will work. The reason that this will work is basically because this equation has a recursive structure. So initially, n is 32, then n is 31, 30, 29, and so on. So in consonance with these equations, this hardware will perform appropriately. So what will happen as I keep on going towards the end? What will happen is that at one point the dividend will start from here. So this entire register here, the V register, will contain the quotient, and what will be left here will be the remainder, right, after we have computed all the quotient bits. Alright, so after all the quotient bits have been computed, what will essentially remain is the remainder in register U, which is what we initially started out to find. So well, an example is worth 1,000 words, so let's do it in a proper way. So let us assume that we are trying to divide 7 by 3. So 7 is a dividend. So similar to multiplication, to avoid overflow issues, we consider a 5-bit dividend. So in this case, our n dividend is 00111 and the divisor is d. So how do we start our algorithm? We start our algorithm by loading the dividend in register V, which is 0111, and we load the divisor into the D register 0011. Subsequently, we will compute our results at 2 points. One is after the shift, which is this point, and one is at the end of the iteration, which is this point. So after the shift, 111 comes here, and x means that this bit we don't care. Then what we do is we try to subtract the divisor from this number, And since we don't have anything, we write a 0 over here. So since the result is negative, will be negative, right? 0 minus any number is negative. We write a 0 here. Fine. Then after the shift, we do a 1-bit shift. So this numbers come here. And the quotient bit that we have computed comes here. Again, we try to subtract 3 from 1. We are not successful. So the next quotient bit we compute to be 0. Again, we do a shift. So this one comes here, this one comes here, this one comes here, and these 2 bits come over here, and one extra space is created where we need to write the next quotient bit. So we see here that 3, the divisor d can be subtracted from 3. So we go ahead and subtract. So at the end of the iteration, we'll have all zeros. And here, since we are able to successfully subtract, we will set the quotient bit to 1. So what we'll have here is 1, 0, 0, 1. Fine, after that we do one more shift. So this one comes here, this one comes here. And since we cannot subtract 3 from 1, 1 will remain and 0 will come here because we couldn't do the subtraction. So the quotient becomes 2 and the remainder becomes 1. Right, which is exactly what we needed to do. That 7 divided by 3, the quotient is 2 and the remainder is 1, and this is exactly what we compute. Right, so the quotient 2, remainder 1, and this is a very simple algorithm. So we just run n iterations. Every iteration involves addition and subtraction, which are order log n time operations. So the total time complexity is n log n coming from n iterations, and log n coming from the fact that we have additions and subtractions in each iteration, and it takes log n time for doing an addition or subtraction. Alright, so this is a textual description of our algorithm. We considered each bit of the dividend. We try to subtract the divisor from the U register. If the subtraction is successful, we set the relevant quotient bit to 1, otherwise we set the relevant quotient bit to 0, and then we left shift. So this is a proof of what we discussed, and since we have already given a graphical proof, students can take a look at this. I'll not cover this, but students can take a look at this part of our description, and they'll get an idea that pretty much what we are talking about. All right, and so this is more of like a formal proof, so you'll find the formal proof in the book, but I just gave a slightly semi-formal graphical proof to which can be further elaborated and written in a formal way, but I'll not discuss that in the current presentation. Alright, so I'm skipping the proof part. So part of the proof, at least graphical part we have covered. The rest, I think the best strategy would be to read the proof from the book and try to correlate it with what's written over here. Alright, so as I said, it takes n iterations and each iteration takes log n time. So total time is n log n. So I'm just, I've taken the O out. So it's order of n log n. Alright, so let's now introduce a new kind of division algorithm called non-restoring division. So here, so what did we see? We saw that we subtract d from u, and we need to restore the value of register u, right? So this is a problem in the sense that we first subtract. If we find that the result is negative, then we need to add the divisor back. So which means we are restoring the value of register u. So this requires either an extra addition, or another approach can be that we'll copy the register u to another temporary location. We will then do a subtraction and then move the values back in. In any case, it's some amount of work. So can we just avoid this? To avoid this, we do something called non-restoring division. So in this case, I'll give the algorithm, the entire structure remains the same. U, V, D, N, everything remains the same. So I'll just give the algorithm. So we do the same thing. We run a loop for 32 iterations. And so this is the beginning of the for loop and this is the end of the for loop. So we do the same thing. We first do a left shift on the UV combined register by 1 position, right? Then what we do is as follows. So this is where, you know, there is a difference. So we first check the sign of u. See, if u is greater than 0, then we subtract the divisor d from it. Otherwise, if u is less than 0, which it can be because we are not restoring, right? So we, you know, in the first iteration, even if we cannot subtract, meaning that the value of u will be less than 0, we still go ahead and subtract. And then in the subsequent iterations, the number can remain negative. So that's the reason in any iteration, if we find u to be negative, we'll add the value of the divisor d, right? So this is one if statement. So what it's saying is that we take a look at the sign of u. We subtract, if it's positive, we subtract the divisor. If it's negative, we add the divisor. After that, if u is positive, you know, positive or 0, we set the quotient bit to 1. Otherwise, we set the quotient bit to 0. And finally, the least significant bit of v, we set the quotient bit, you know, q, the number that we computed, that is set to the least significant bit of v. And so this is the way that we do this algorithm. So what we essentially do is that we don't do any restoring. If u becomes negative after a subtraction, we allow it to remain negative. And in the next iteration, we just add the divisor. So that's the way that we you know, go. That we, if u is positive, we subtract. If it's negative, we add. And after that, we take a look at the sign of u. If u is positive or 0, we set the LSB of, you know, the current bit of the quotient to 1. Otherwise, we set it to 0. So after all the 32 iterations are finished, if we find u to be less than 0, then we set u equal to u plus d, or u plus the divisor. So at the end, the lower 32 bits, so u is a 33-bit register, again to avoid overflows, right? So at the end, if u contains the remainder and v contains the quotient. All right. So before giving the insight into why this algorithm works, it's slightly complicated, but it's there in the book. Let us understand via an example how this works. So let's again try to do the same division, which is divide 7 by 3. So we start with loading the dividend in the register v, and the divisor can remain in register d. So in the first iteration after the shift, we basically shift the 3 bits 1, 1 and 1 over here. And then what we do is, since the sign of this, so since this is a positive, this number is positive or 0, we subtract the divisor. So well, subtracting the divisor means adding its 2's complement. And so this is the 2's. So I can just, so this 1, 1, 1, 0, 0 plus 1. So this is the 2's complement of 3. So it's minus 3. So after this, the sign of this number is negative because the sign bit is 1. So hence we set the quotient bit, right, qn to 0, q4 to 0. Alright, so after this we perform one more shift. So we have 1101. So 1101 gets shifted to here. 1 gets shifted here, and here we have 110, and we have one bit that we'll fill later. So this number is negative. Since this number is negative, what we do is that instead of subtracting, we actually add the divisor. So we add 1, 1, 0, 1, 1 plus 1, 1. So 1 plus 1 is 0. 1 plus 1 plus 1. So 1 is the carry. 1 plus 1 plus 1 is 1. 1 plus 0 is 1. 1, 1. So we have 1, 1, 1, 0. So again, this number is negative. So the quotient bit that we set is 0. Now we do one more shift for the third iteration. So 1110 gets shifted by one position. This 1 comes here and 100 gets shifted over here. This number is again negative, so we add 1 once again. So 11101 plus 1 is 1 plus 1 is 0, carry is 1, 1 plus 1 is 0, carry is 1. 1 plus 1 is 0, carry is 1, 1 plus 1 is 0, carry is 1, and again 0. So you're left with all 5 zeros. And this number, mind you, is 0, right? It's positive or 0. So we'll set the quotient bit to 1. Alright? So the relevant quotient bit is set to 1 because our variable q in that algorithm is 1. Fine, we do one more shift. So we set, so 1 comes here, 001 comes here. And so since this number is positive, we will subtract the divisor. So subtracting the divisor means adding its 2's complement, which is 11101 plus just 1. And so then this becomes 1 plus 1 is 0, carry is 1. Right? So this becomes what we need to have. And since this number is negative, we set the relevant quotient bit to 0. So now the quotient is nicely saved in register V, which is 0010, which is 2. So the quotient is correctly computed. That's 7 divided by 3. The quotient is 2. This is correct. However, we find that the register U, so if you consider the last line, we have said if U is less than 0, then we add the divisor to U. So in the last line here, register U is negative because the sign bit is 1. So we need to add the value of U. So we need to add U as U plus D. So the way that we do is we add 1110 plus the divisor. So this is 0 plus 1 is 1. 1 plus 1 is again 0, carry a 1. So the rest will be all zeros. So that's the reason we see 001 here. So 001 is the remainder, right? So the remainder is 1 and the quotient is 2. So in this case, it is not that we change the ultimate asymptotic complexity of the algorithm. We didn't do that. So we still have n iterations. So the time required is order n. We still have n iterations, right? And in each iteration, we at least have a subtraction or an addition. So that is log n time. So we still require order n log n. But it's just that we don't restore the value of u. So we either do an addition or we do an subtraction, but that's it, right? We don't do anything more. So that's the reason this is called a non-restoring algorithm, which is again a standard and very popular algorithm. And the non-restoring algorithm is regarded as a standard. So it is used in many processors for division. And the algorithm is again, just to summarize, we take a look at the register U. If it's positive, we subtract the divisor, else if it's negative, we add the divisor. We take a look at the sign once again. So if the sign has become, if the sign bit is 0, which means the number is non-negative, we set the relevant quotient bit to 1, otherwise we set it to 0. We perform a small check at the end. If the register U is still less than 0, we add the divisor to U and U contains the remainder and register V contains the quotient. Alright, so now let me give an idea, a very brief idea of the proof, but the detailed proof is there in the book. So it's not really, the proof is slightly involved. It's also, so that's the reason it is kind of difficult to explain it via a presentation, but let me nevertheless try. So let's assume that u minus d at some point is greater than or equal to 0. So both the algorithms restoring and non-restoring will produce the same result and we'll have the same state, right? Now assume that u minus d is less than 0, then both the, so the way the proof is going is that we are trying to say that our results will be the same as that of the restoring algorithm. Since the restoring algorithm is correct, we are also correct. So we are saying that let's start from the beginning. if we can subtract d from u, we are at the same state. Otherwise, we diverge. We go on one path and non-restoring. Restoring goes on one track and non-restoring goes on another track. So in the restoring algorithm, the value of the UV register, discounting the quotient bits, let it be A. In the non-restoring algorithm is A minus, the divisor sort of shifted by n bits. So A minus 2 to the power n d. So where is this coming from? This is coming from the fact that in our UV register, U and V, if I consider the divisor, it is from the beginning of the V register, where you're assuming all the temporary quotient bits are all 0. This is, in a sense, left shifted by n positions. So that's the reason 2 to the power n comes. Now in the next iteration, just after the shift, so we'll multiply the number by 2, so it will become 2a. So in non-restoring, in the restoring, the number will become 2a. In non-restoring, the number will be 2a times 2 raised to the power n plus 1 times d. So whatever was there in the previous iteration just gets multiplied by 2. Now at the end of this iteration, if the quotient bit is 1, then we will subtract 2 to the power n times d in the restoring algorithm to get the value of uv, discounting the quotient bits, of course, as 2a minus 2 raised to the power n times d. In the non-restoring algorithm, we will add 2 to the power n times d. So what we will get is 2a minus, so this is what we began with, 2a minus 2 to the power n plus 1 times d. Since we are negative, we'll add 2 to the power n times d. So what we will get is, we'll get this. So as we can see, this is equal to this, which means that whenever we set the quotient bit to 1, the state of the restoring and non-restoring algorithms becomes the same. And so since the restoring algorithm computes the right results, we also compute the same set of results in terms of both the quotient as well as the remainder. So mind you, my proof is slightly hand wavy in nature, the main reason being that the book has a more detailed proof, and in a presentation is just my aim is to give a very, very high level overview. So again, just continuing in an overview style, whenever we set the quotient bit to 1, we will find that the value in the UV register, discounting the quotient bits between the restoring and non-restoring, will be the same. Otherwise, the quotient will also keep set, the restoring algorithm will continue to set the quotient bits as 0, and the non-restoring algorithm will continue to also set the quotient bits as 0, and whenever the quotient bit is set to 1, both the algorithms will have the same state, in the sense all the registers will have the same set of values. Now let's say at some point, if the quotient bit is 0, then the partial dividend n dash in the case of restoring is 2a, and in the case of non-restoring is another value. So like that we can keep going, but we can easily prove that whenever the quotient bit is set to 1, the states of both the restoring and the non-restoring algorithms become the same. Alright, so I explained two kinds of algorithms, restoring and non-restoring, and with the help of this example, where the slide deserves to be cleaned up. So with the help of this example, we explained how to divide 7 by 3 and compute the quotient and the remainder. So in this context, two algorithms were discussed. Restoring and non-restoring. So in the restoring algorithm, one subtraction needs to be done in each iteration and one addition. Alternate versions are possible, but still a fair amount of work needs to be done. Right, so essentially here one subtraction and one addition needs to be done. But in the non-restoring version, either you do a subtraction or you do an addition, but not both. So in that sense, the work is roughly halved. That's the reason the non-restoring algorithm is used. And the way that you prove it works is that you start, so the first state is the same. After that, what we need to prove is that every quotient bit is computed correctly. And whenever a quotient bit is computed to be 1, the state of both the algorithms is the same. You know, the values of all the registers is the same. So pretty much we can say that, let's say that we compute the quotient bit to be 1, right? Maybe small q. After this, as long as the bits are being computed as 0, the algorithms will take 2 separate paths, right? In this entire region, the quotient bit is being computed to be 0. Finally, when we again compute a quotient bit to be 1, the states merge. Then again, if the quotient bits are 0, the states diverge. Again, the next time that the quotient bit is 1, the states will merge and be the same. So that's the way that we can prove. The detailed proof is there in the book. But in any case, the summary is that the non-restoring algorithm is faster than the restoring variant. So now we shall take a look at floating point addition.